Hello guys, so let's discuss today's POTD, that is 3607 Power Grid Maintenance. So it is marked as medium. You are given an integer C representing C power stations, each with a unique identifier ID from 1 to C, 1 based indexing. These stations are interconnected via n bidirectional cables represented by a 2D array connections, where each element connection I is equal to UI VI indicates a connection between station UI and station VI. Stations are directly or indirectly connected form a power grid. So what this para is saying that there's a connected, you can say a connected undirected graph, and if a component of this graph will called a power grid, and all the elements present in it, they will be connected directly or indirectly. And also there might be some components which are not connected. For example, there might be this is one component, means it is a one power grid, and if there is a 6 present which is not connected, then it is also another component, so means we have two power grids. So this para is saying that initially all stations are online. So this is important line, means initially all the stations are online, and you are also given a 2D array queries where each query is one of the two following types. One X, it means that a maintenance check is requested for station X. So if it is 1, then it means the check is requested for the given X. If station X is online, it resolves the check by itself. So the problem statement is very important, means we have each line is very important in this problem statement. If station X is offline, the check is resolved by the operational statement with the smallest ID in the same power grid as X. If no operational station exists in that grid, return -1. So if a station X is online, initially we know that all stations are online. So if a station X is online, then we have to return the station is as the answer for this query. And if the station is offline, then we have to find the smallest station, means the smallest value in that power grid, in that component, and we have to return it as our answer. And if there is no operational station exists, means the component is empty, then we have to return -1. Then the second type of query is that station X goes offline. If there's this 2X given in the query, then the X will go offline, means it becomes non-operational. That is obvious. Return an array of integer representing the results of each query of type 1, X in order they appear. So we have to find the answer for this type of query. Note the power grid preserves its structure. An offline node remains part of its grid, and taking it offline does not alter connectivity, means the component will still be connected, mean the component will not disconnect if a station goes offline. Let's understand it with this example. So the C is given 5, means we have 5 stations, and the connections are given this, and the queries are given this. So the connections, we have made a graph for by using these connections and the queries. Let's see the queries. 1, 3 means we have to perform the type 1 query for station 3. Since all the stations at the starting are online as given in the problem statement, so for this the answer will be 3 itself. This is 3, and the type 2 query is this is type 2 query, and we have to make offline. This station will go offline, one station, so it will go offline, and we don't have to perform we don't have to return any answer for this query. Then this is type 1 query, and we have to find for the station 1. since the station 1 is goes offline in this, so we will not return 1 as the answer, because this one station goes offline. Now the next thing what we can do is the minimum element present in this power grid. So what is the minimum element present in this power grid? That is 2. So we will return 2. This type 2 and the type 2 query, and the which we will perform for station 2, and through this query the station 2 will go offline, and then we have to find the answer for our station 2. This is a type 1 query, and we have to find the answer for this. And the smallest element present in this power grid is 3, so we will return 3. I hope this example test case is clear, and I have explained the problem statement also. So one thing what we have to do is we have to keep the track of this. We have to keep the track of which station goes offline. So we can use set for this, that which station goes offline. I'm explaining the first approach, or the what I was thinking when I was solving it. So the first thing that came in my mind is let's define set for this to keep track of the offline stations. Set for offline stations. Okay, now the next thing is what we can do is we can put these elements, means we can put the elements of a power grid, means of a component. We have to keep this elements with ourselves. So means for this power grid the elements are 1 2 3 4 5, 1 2 3 4 5. So we have to find a way so that we can when we are doing the operations, we can find that this element is present in which power grid. So for that what we can do is we can create a map, means for suppose this one we can create a map. And what else we can do, we can connect this map through the parent, means if suppose this is a connected component. Let's understand it this way. This is a connected component. So what we can do, we can find the parent for these elements. So the parent for 1 will be 1, 2 will be 1, 3 will be 1, 4 will be 1, 5 will be 1, because this is a connected component. So the parent for this is 1. So now what we are doing in our map, the key will be our parent, and corresponding to the parent key we will store the elements of this parent. So we will store 1 2 3 4 5. Okay, and suppose there's another component that is suppose this is a 6 7 8 9. So the parent for this is 6, for this 6 6 6. We can take we can take any element as a parent, but we are taking 6, so let's see this way. So for the 6, the elements present are 6 7 8 and 9. So this will be our map, and we will store these elements in a set. Why? So that we have to find the minimum element also. If suppose any station goes offline, then we have to return the minimum element. So so why we are storing it in a ordered set, so that we can find the minimum element in O of 1. The first element will be minimum. Okay, so this is our map. So now what I will do is I will do I will iterate in this queries, means I will traverse this query vector and I will check for each query. If it is a type 1 query, then I will check the parent of this station, and we have a parent, obviously we will have a parent vector also for each element. So the parent vector, this is the parent vector: 1 2 3 4 5 6 7 8 9. So this is the parent vector. For 1 the parent is 1, for 2 1 3 1 4 1 5 1 6, for 6 the parent is 6 7 6 8 6 9 6. So this is a parent vector. So for each query I will see the type of that query, and I will find the parent of that station. So the for this 3 the parent is 1, then I will go in my map and I will find whether this station is present in this set or not. If this station is present in this set, that means this station is operational, that is online. So I will return that station itself, and if this station is not present in a set, then I will return the first element of that set. This is for the type 1 query, and for the type 2 query I will do the same thing. I will find the parent of this station, that is 1, and I will go in my map to see the corresponding elements. Means 1 is present in my set. So I will erase this, and I can erase it O of 1 time. So this will be also a good thing for all to store these elements in a set. That's why we have used this set thing. So I can do both the operations in O of 1 time, both the queries in O of 1 time. So this is the approach. I hope it is clear. Now let's move on to the coding part. So what I am doing is I am doing the same thing that I told while explaining this approach. So I have declared an answer vector, and this is a irrelevant thing because we are not using this offline. We are simply erasing it in our set. So, and we don't need this offline also, means offline station we don't need for any operation, for any further results. It is independent, so we will not use this offline one. Okay, so this is, but at first like this, why I told you that about this offline set, because this is the first thing that came in my mind while solving it. So that's why I've told you. So we will not use this, and now what I'm doing is I'm just finding the components. So I have created an adjacency list, and this adjacency list for undirected graph, and also I'm putting this in the same element in my adjacency list. Now what I've created a map for storing this, which stores the key and the set. So this is for a map. This is the map for storing these elements, and then I'm creating a parent vector. Okay, now what I'm doing is I'm just finding the component, a connected component. So I'm traversing from 1 to C, and if the parent is 0, that means this element has not any parent currently, and it is not visited also, we can say. And now I'm calling the DFS with this current node, that is current value, current parent, this parent factor, adjacency list, and the set, and I'm storing the set that I will get from this function in my map corresponding to the current node key, as current node as a key. So let's go to the DFS one. So in DFS I am doing the simple DFS. If the parent I means the current element is not visited, then current element is visited, then I am returning and otherwise I am putting the parent of current element as the parent of this whole component, and I'm inserting it in my set, and I'm calling the DFS for the DFS for this. So this DFS is simple. Now so from here till here I got all this thing, means I got elements in each component. Now I am traversing the queries, and this OP means which type of query it is, and the station, which station it is. And if the query is type 2, then what I'm doing is I'm finding the parent for the station, for this station, and I am erasing the element from my map for the for this current parent key. Otherwise I am this finding the parent for the current station, and if the size for this is 0, then means there is no element present in our set, so I am returning -1. So this case, it is this case. If no operational station exists in the grid, return -1. Otherwise I am finding the station. If the station is present in my set, then I am putting it in my answer, that station itself. Otherwise I am putting my this first element of the set in my answer. At last I am returning the answer. So let's see the time complexity. The space complexity will be O of n. We are using here for this answer vector. O of c is we are using for this this adjacency list, to making the adjacency list, and we are also using for this map O of n. This will be approximately O of n in the worst case, let's assume, and here also O of n for the parent vector, and we are also using the set. So the space complexity will be approximately O of c, that is this given stations. So the approximately this space complexity will be O of c, and the time complexity will be, I'm using the O of n here in the connection size. Let's assume the O of c. So O of c here and O of c here. Since it is a map, and also this is set, so set will take the log n operations for each element, and there are c elements, so c log c will be the for this set operations, and this for DFS. And now I'm treating here also for inquiries, and it will also take the O of c. Then I'm erasing this will take O of 1. All these erase operations and find operation, this will take O of n. So the overall time complexity will be O of c log c. Approximately this time complexity will be O of c log c, and the space complexity will be O of n, O of c. So yeah, this is the solution for this problem. Thank you.